Hello, welcome back. Today we're going to be going over a few different ways you can measure the performance of a machine learning model. And in the previous video, I went over overfitting and underfitting and how you can use your performance measurements to determine whether your model is overfitting or underfitting. Here I'm going to be going over a few of those possible performance measurements that you could use and why you might want to use them and why you might not want to use them. So with that said, let's start this. So before we can go into any of these performance measures, we need to talk about four different things. We need to talk about a true positive, a true negative, a false positive, and a false negative. So what do each of these options mean, and how can we get them? So to get these options here, you want to think about a truth table of sorts. So if we have a table that we want to make, and it has four options. So everything, the two columns pertain to actual values, and the two rows pertain to the predicted values. And then for each of these, we can think of these as being a true predicted label, a false predicted label, and then a true actual label and a false actual label. So then these different cells here give us these four different values. So for example, this here is the true positive because we correctly identified a positive label, a true label. So it is a true positive. Over on the top right cell, we have a false positive. So we actually had a false label, but we predicted it to be positive. So it is a false positive, one that was predicted positive when it should not have been. In the bottom left, we have the false negative. So it was a true label, but we predicted it to be false. So it is a false negative in this case. And then finally, we have the true negative. So in this case, we had correctly identified a false label. The actual label was false, and the predicted label was false. So it is a true negative. So these four values here, these four cells, are what's going to make up all of the performance measures that I will be going over. And what we do is, you will go, to calculate each one of these, you would go over every one of your data points, and you would say, okay, is this a true positive, false negative, or true negative? And you would slowly sum up. So in the end, after you've gone over all of your different data points that you might have something like this, where maybe you have 53 true negatives, maybe 23 true positives, and then hopefully a small number of false positives and false negatives. So in this case, if this was our data set that we had, we correctly identified, this is what this would mean, we had correctly identified 76 different data points, and then we misidentified, so we failed to predict on 20. So our total data set is 96 data points, and out of that we correctly predicted 76 out of those 96 data points. So this is how you would get these different values. And then from here, we can go and actually calculate the three different performance measurements, 3 to 5, depending on what you find useful. And we can go through and talk about what those performance measures are then. So with that, I actually will move into accuracy. So what does accuracy actually mean? Well, first things first, to actually calculate accuracy using the true positive, false positive, and so on labels, is you would have true positive plus the true negative over true positive plus true negative plus false positive plus false negative. So basically everything correctly predicted up top, so all of your correct predictions over all of your predictions. So it's just a normal accuracy percentage that you could have. So you could say if you might have an accuracy of, say, maybe 80%, where altogether these up here, your true positives and true negatives, would equal 80% of your data set. So that's what this could be. Now, why might you not want to use accuracy? Well, normally you actually should not use accuracy, and the meaning for that is because of skewed data sets. So if you have a data set that has a lot of a particular label to it, so if you have a data set that's, say, mostly 90% positives, positive labels, and you go to predict on you build a model off of that and you predict on it and you get, oh, it has 90% accuracy. Well, does it really have 90% accuracy, or is it just that it predicted positive the entire time, so whenever it gets a false label, it's always false? So for example, if we say do something like this, 1, 2, 3, 4, 5, 6, 7, 8, I'll go over here, 9, and 10. So if we have actual labels here, so actual labels, we have 9 true and 1 false, and then our predicted are all true. So in this case, we would actually see that we would have 90% accuracy, because out of the 10 data points, it predicted correctly 9 out of the 10 of them. But the key part of this is that how it predicted that one wrong data point. And from this, we don't know. You could very well have just made a model that always predicts true, and so if you ever do get a false label, it might just always predict false. So in the real world, if you go and send this model out and come to find out most of the labels that come in to predict on your model are false, you would have a horrible model that would almost have 0% accuracy. And so yes, you can adjust and add more data points over here to your actual, and that would help this imbalance, but sometimes you cannot find new data points to add. And so it's best to just avoid accuracy altogether and use one of the other 2 performance measurements that I'll be giving next, as those offer more insight into maybe not just how well the model performs, but also why it performs in such a way. Now, next on the list of performance measures is the F1 score. Now, the F1 score is actually made up of 2 smaller performance measurements. The first one being, so first is F1 score. So the F1 score is made up of precision, and recall. Or I'll just put down here, say P and R. So the F1 score is calculated by 2 times P times R over P plus R. So that is how you calculate the F1 score. Now this here is actually special. It is a special formula where it means that we are calculating the harmonic mean of precision and recall. And so the harmonic mean is a little bit different than just a normal mean. So with a normal mean, you would just have P plus R divided by 2. That would be the normal way to calculate the mean for these two values. But the harmonic mean is a little bit different in that it actually takes a real difference between the precision and the recall. So if one is overbalanced of the other, you can actually tell that. So for example, if you have a 0 precision and a 1 recall, it's not going to just be 0.5 as your mean. It would be something different. So now, why would you want to use the F1 score over, say, accuracy? Well, as I mentioned before, it is very, very helpful for skewed data sets. That is one thing that the F1 score is actually very helpful with. It is also very good with multi-label data. So for example, if you say are calculating grades for a student or for a class, for different students for a class, you would have, say, an F, D, C, B, and A. These would all be different labels for that class. And so to calculate the F1 score for these, or to calculate any of these performance measurements, you actually have to go in and calculate the true positive, false negative, and true negative values for every one of these values. So you would get those values for A, those values for B, those values for C, and so on. And the way you would do that is, say we'd be wanting to calculate A, then what you might have is you might have something like this, where all of your data, all of your labels that you would see in your data set would have zeros for F, D, C, and B, and then 1 for A. And so it will go through and say that A is a true label and all the other ones are false. And then it will calculate those 4 values that I mentioned. And then it will do the same. It will set B equal to 1. And then everything else is 0. And it will go through and do that as well then. And so that's how you would that's how you would then calculate the F1 score for each one of these values. Now, they're again going for all these different options for a multi-label data set at least. Something that you need to think about is how you would bring these together. So this is just a little tangent here, but if you say you have these two options. You have micro averaging and you have macro averaging. So if you work in, say, with sklearn in Python quite a bit, you will see these come up for the different performance measures. And so what micro means is that it will go through and calculate all true positive, all true negative, all false positive, and all false negative values for each one of these labels here. Then it will sum up all of the true positives, all of the true negatives, and so on. So you would actually get, for say, if you were looking at accuracy, it would calculate the sum of all true positives plus the sum of all true negatives over the sum of all true positives plus the sum of all true negatives, and so on. So that's what the micro average for a multi-label dataset looks like. And now the macro average is it'll go through and calculate your actual performance measurement, then average them all together. So now, for example, we would have, say, the F1 score for A plus the F1 score for B plus the F1 score for C, the F1 score for D, and so on, divided by, you would have the 5 values. And so this would be the macro average then. So it depends on how you want to calculate. If you do have a multi-labeled data set, this is something to keep in mind. Usually I stick with the micro because, again, thinking of, it's always nice to assume that you have a skewed data set, even if you think you do not. It is just best to assume that. That way you don't accidentally take up any false or bad habits doing of calculations. So I usually stick with micro because micro is better with skewed data sets, especially in this case for multi-label skewed labels. So if, say, the majority of your labels were A, then micro would be a better option. Whereas perhaps if they were all even, say if you had 5 of each letter in your data set, letter grade, then you could use macro if you wanted to. So that little rant aside, that's micro and macro for multi-labeled data sets. And I will separate that out. But now going back to the F1 score, it's also very good if you want to focus on precision and recall. So as I mentioned, the F1 score is the harmonic mean of precision and recall. And I know I've not gone over those two, and I will here in a second. But so if you are focused on precision or recall, or I should say and recall, then this is what you would want to use. Now, if you are focused on just one of these, then you might just want to choose one or the other. You don't necessarily need the F1 score for both if you're not needing both. But that's overall the F1 score. So now I've just talked quite a bit about precision and recall. So what exactly does precision and recall mean? So for precision is calculated by, so P is equal to, if we're going back to the true positive, false positive, and so on, the precision is equal to the true positive rate over the true positive plus false positive. So another way to think about precision is you want to see how often your positive predictions are correct positive predictions. So another way to think about it is if you look at all of your positive predicted values, how many of those are actually positively labeled. So it's another way to think about it is that you are trying to look at how well your positive labels are being predicted. And then for recall, which is also known as sensitivity. So you'll see it's interchangeable. Recall means sensitivity, sensitivity means recall, and so on. So the recall is equal to the true positive rate over the true positive plus the false negative. So the recall then is trying to see how many of your actual labels that were positive were predicted for positive. So for P, it's good to think about and then for recall, so that's how you can think of both of these. And there are better explanations out there, I will admit that. if you do want a better explanation, and what I can usually go back to if I forget these precision recall explanations, is a very, very nice Stack Overflow answer that I will have linked in the description that not only goes over the false positive, or not, it not only goes over precision, recall, but also it goes over the F1 score and receiver operating characteristic, which is what I'll be going into next. So if you want more help on figuring out what all this means, then I would suggest going into the description and seeing that Stack Overflow answer that I'll have linked down there, because that does offer, it has offered me some good help in the past. So now, finally, I will be going over the receiver operating, oops, that's a no, operating characteristic, or ROC. So now, what does the ROC mean? So a good way to think about the ROC is you can think about it as multiple F1 scores, and that you are plotting, more specifically, multiple F1 scores. So before we even go into what the X and Y are here, we could say you might have an ROC that looks like this. So you would have an F1, each one of these different grids here would be a different F1 score. So that's how you can think about what the receiver operating characteristic is you are calculating multiple F1 scores by shifting what's called a cutoff value through your data. So now, since you know that the receiver operating characteristic goes over multiple F1 scores, how are they calculating what is this X and Y here? So the X-axis is 1 minus specificity. And the Y-axis is the sensitivity. And if you remember, I mentioned earlier that recall was sensitivity and vice versa. So you could even say that this is recall as well. Both of these are equal. And so what you're figuring out here is you are plotting the basically false positive rate. Oops. The false positive rate by the true positive rate. Again, I write an R. True positive rate. So you're plotting the true positive rate compared against the false positive rate over multiple F1 scores. So that's what this receiver operating characteristic is. Now, how are you getting these different F1 scores though? How are you figuring out what this cutoff is? Well, first you need to think about what data you are using. So the receiver operating characteristic, first off, is only, again, just like with the F1 score, is only good with the true positive, false positive, and so on values. So what you need to think about is you want to look at your actual values here. So we might say actual, maybe you have some true, true, false, true, false, something like that. So you have your actual labels situated. And now for your predicted, the predicted are not labels. They're more so of a score, so to speak. So you might have, for this true label here, you might have, say, 0.89. For this true, you might have something like 0.23 or something like that, and so on. So another way to think about it is your actual true and false labels were not originally labels, so to speak. So you might have had maybe your labels were, say, 0.73, 0.82, and so after you go through and you train your model will be outputting these scores, but you would have your actual scores be converted into their true and false labels. So you would have some sort of cutoff associated with these inputs. So maybe for this, the cutoff would be maybe 0.65. So the cutoff in this case might be 0.65. So any of these actual labels here that are above 0.65 or above would be set to true, and any label that's under the 6.5 is set to false. And so that's how you get these true and false actual labels. So this is what goes into creating the ROC curve. If you look at the sklearn library function call for ROC curve, you are giving it your true and false labels, as well as a score that your model is exporting. So that's what that's what you want to use for your receiver operating characteristic and how you calculate it. Now this cutoff value here is the key point. So when you give these actual values here, these actual labels, those are set in stone. Those do not move. Those are baseline actual labels. And then you can think of these predicted labels here as being variable. They have their own cutoff. And so when you go to calculate the ROC curve, it will actually calculate multiple different cutoffs for these different labels. So maybe the cutoff values might be like 0.2, 0.35, 0.4 or 4.5, and so on. So these might all be different cutoff values. And so what the algorithm would do is it would take each one of these cutoff values and generate a set of true and false labels for your predicted input. So example for this 0.2, both of these labels here would be considered a true label because this 0.23 is above 2, so it would be considered true, and obviously this 0.89 is also above 2.2, so it's also considered true. Whereas if it would move on to the next cutoff and have it set to this 0.35, it would have this 0.89 be true, but then this 0.23 would be false. And so that's where your predicted scores are converted to predicted labels, true and false labels. Then once those labels are converted, it then does the true positive, false positive, true negative, and false negative values using the now predicted labels and the actual labels. So in the end, each one of these cutoffs is going to have these true positive and true negative and so on values associated with them. And then ultimately each cutoff value is going to have this true positive rate and false positive rate calculated. So now it would have a list of these true positive and false positive rates. So maybe it would have, say, a true positive, so TPR, and false positive rate FPR. Maybe this 0.2 would have a true positive rate of 0.89 and maybe a false positive rate of 0.2. And then so on down the list for each of these cutoff values. So you would have one for 0.35, you would have one for that, and then you would have one for 0.45, and so on. So once you have these values, then you go and sort them. So when you go to return these values, say if we're looking at the ROC curve function from sklearn, for example again, its return is a list of sorted true positive values and sorted false positive, or true positive rates and sorted false positive rates, and a sorted list of their thresholds. And when it says thresholds, it's talking about these cutoff values that I've been talking about. And when it's sorted, it's in a sorted order such that you get this curve. So you'll notice that this true positive rate and false positive rate slowly will go up. So this, say if we're looking at a point for an example, this point here might be 0.2, this point here might be 0.35 or I'll say 0.45, and this point here might be 0.35. So these cutoff values and subsequent F1 scores are not necessarily in order on this plot. That's something to note. Each one of these F1 scores here are not or may not be in order. They're just in order of value in order to get this graph. Now the question is, what's the best and what's the worst ROC curve that you can get? Well, the very best curve that you can get would look like this. This would be the best ROC curve, where your true positive rate goes up to pretty much instantly, goes up to 1, because that should be something I should note here. Each of these starts at 0.0 and then goes to 1.0. So this whole chart here, this whole plot its domain is 0.0 to 1.1 in both the x and the y-axis. So you would want it to instantly go up to 1.0 very soon, and then stay at 1.0 the entire time that it's going across the x-axis. That basically means that the true positive rate is always 1, so it's always correctly predicting the true positives at the same time that the false positive rate does not increase. or at the same rate, I should say, the same rate that the false positive rate also increases. So this would be the best ROC curve. Now the worst ROC curve, and what you would usually see when you are seeing these plots, is you would see something that looks like this. It would be a dashed line, and I have it here in blue. You would see a dashed line like this, and this dashed line corresponds with chance. So as you go along here, it would be following basically, its slope would be 1. It would start at 0, go up to 1.0, 1.0, 1.0 on the chart, and it would have a slope of 1. And this corresponds to chance. So if your ROC curve is on this line here, is on this blue dashed line, that basically means that it's randomly predicting, and you won't have it's not a good model. That's about the worst that it can do. And so this is generally what you are looking for with an ROC curve. Now, as I mentioned with the F1 score, you can average F1 scores together. You can average these ROC curves together. So if you have a multi-label data set, you can average multiple curves here and get one single ROC curve for all of your labels together. Or another thing you can do, which is possibly more preferred, is to keep all of your labels separate and then say have a different, something like maybe this. You might have a few different lines like that for your different labels. So each label would have its own unique line in your ROC curve. Those are your two options that you have. And when you do average them together, you have that same micro and macro options available to you. Now there's something else that you can do with this ROC curve. Say you do actually want, this might be a little bit hard to visualize, and you want to actually get a real single number out, like an F1 score. Well, what you can do is called an area under the ROC curve. So this area under part here refers to all of the area associated underneath this curve. So what you would do is it would calculate the area under this curve and give that back to you as a single output. So that's what this area under the ROC curve is. And usually what you might find is in a plot, an ROC plot, in the legend, you might have the area under the ROC curve as a number associated with each line on the plot. So that's something that just kind of good to know that you might see with these plots when you see them. Now, something to note, yes, you can use with multi-label datasets. However, it's not preferred to. If you do have a multi-label, multi-class dataset, it is preferred to use the F1 score. That is something to know. But if the specificity here, or more specifically the false positive rate, 1 minus specificity, is what you're interested in, and maybe not so much precision, you don't care as much about precision, this would be something that you should still look at. And you can have both. You can have both an F1 score and an ROC curve. That's not a problem. That's two ways of looking at it, and they both have their merits. So you might even have both looking at, when you're viewing your model's performance, you might have both listed and you might need to talk about which one is more important to look at. So with all of that said, that's all of the measures of performance that you can have. And so with that, that's all I have for today. The next video is the last video in the series. It will be going over cross-validation. And once you are done with that video, you should have a very basic understanding then of machine learning, how to get started, where to look, and how to look at different problems. So with that, thank you very much, and bye.